In this lecture video, we're going to continue our introduction to the basic concepts of statistical inference. Now, in the last lecture video, we looked at hypothesis testing. In this video, we're going to be looking at estimation, and we'll start off with point estimation. So a point estimate is a number that represents a guess as to the true value of the population parameter being estimated. Not only is it a guess, but we can say that it's a data-based guess. It's an informed guess based on the data that we've obtained from the population about which we want to make inferences. Now, we hope that the point estimate will be close to, but we know that it will probably not be exactly equal to the population parameter being estimated. Now, there are two fundamental questions when it comes to point estimation, and they are the following. How do we come up with a point estimator for a given estimation problem? And if several point estimators are available, which one should we use? Now, there are two popular methods for coming up with point estimators. The first is method of moments, and the second is maximum likelihood. Now, you probably have heard of the second, maximum likelihood. If you've heard of maximum likelihood estimation, or MLEs, then you have heard of maximum likelihood, but you may not have heard of method of moments. Now, in a given estimation problem, there may be several potential estimators available. In such a situation, which one should we use? In order to make this determination, we need to be able to compare the estimators. This requires criteria with respect to which the estimators can be compared. Now, two important criteria that should be considered when evaluating point estimators are the biasness or unbiasedness of the estimator and the reliability of the estimator. Now, biasness or unbiasedness gets to the accuracy of the estimator, and reliability goes to how close we can expect the estimator to be to the true value, and also in terms of its, it speaks about its repeatability. Now, in addition to point estimation, we also have confidence interval estimation. A confidence interval estimator is a range or interval of plausible values for the population parameter being estimated, along with a measure of the reliability of the estimation procedure itself. Now, this measure of reliability is called the confidence coefficient, or the confidence level, and is expressed as a percentage from 0 to 100%. Now, a confidence interval estimator is obviously not as precise as a point estimate, but it has a high degree of confidence, or we have a high degree of confidence, that the parameter being estimated will be contained in the interval. Now, the confidence coefficient, or the confidence level, is a value that we choose, and we choose that when we construct the interval. Now, typical values of confidence coefficients or confidence levels, which again are expressed as percentages, are, let's say, 90%, 95%, 99%. Now, when we think about the confidence coefficients, we have to be careful about how we think about this. It's not really correct to think of this as a probability that the confidence interval contains the parameter being estimated, at least if we think about that as a conditional probability based on the data. Now, we could go into more detail about this because there are some valid ways to think about it as a probability, but we want to be careful and not misrepresent or think about the confidence coefficient incorrectly. So for now, we'll just say that it's a measure of the reliability of the procedure used to construct the confidence interval. The higher the confidence level, the more confidence we have that the interval that we've constructed from the data actually contains the parameter of interest. Now, the confidence limits are the endpoints of the confidence interval. The lower confidence limit is the left or lower endpoint of the confidence interval, and the upper confidence limit is the right or upper endpoint of the confidence interval itself. Now let's talk about confidence interval width versus the precision of the interval. Now, confidence interval width and confidence interval precision are inversely related. In other words, wider confidence intervals are less precise, and narrower confidence intervals are more precise. Now let's talk about what we mean by a margin of error. So in many situations, specifically and in particular, when using procedures that are based on an assumption of normality or of a normal distribution for the underlying data, we construct the confidence interval by starting with a point estimate and then computing the lower and upper confidence limits by going a certain distance to the left and to the right of that point estimate. This distance to the left and to the right of the point estimate is called the margin of error. Now, when using a non-normal based procedure, it will not make sense to talk about the margin of error in those kind of contexts because we don't construct the confidence intervals in the way that we just described up here. We use a different kind of approach. Now, the general form of a confidence interval with a confidence coefficient or confidence level, which we will denote by 1 minus alpha times 100%. And so how do we construct a confidence interval, or what is the general form? Well, again, in cases where the sampling distribution of the point estimate is at least approximately normally distributed, the confidence interval is of the following form. And this is just a more mathematical way to represent what I said on the previous slide. We start off with a point estimate, and then we go a distance to the left and to the right of that point estimate, that distance being the margin of error. All right, and so this is how we would calculate the lower and upper endpoints of the confidence interval. We would take the point estimate minus the margin of error, that would give us the lower endpoint, and then take the point estimate plus the margin of error to obtain the upper confidence limit, the upper endpoint of the interval, and that would give us our what we call a two-sided confidence interval. Now, in order to do this, not only do we have to know how to calculate the point estimate, but we have to know how to calculate the margin of error. And the general form for a margin of error, at least if we're basing the confidence interval on normality or approximate normality of the point estimate, is that it's the product of what is called an interval coefficient, a value from the standard normal table, and then the other term in the product is the standard error of the point estimate. So the point estimate is computed from the sample, from the random sample. It's a random variable, therefore, and so it has a sampling distribution, and that sampling distribution has a standard deviation. And you'll remember that we call the standard deviation of the sampling distribution of a statistic, we call it the statistic's standard error. And so that's what we're talking about right here. Okay, so this point estimate is a random variable. It has a standard error. And so to obtain the margin of error, we multiply the standard error of this point estimate by this interval coefficient denoted by z sub alpha over 2. Now, what is this z sub alpha over 2? Well, it's defined in the following way. So if we let p be the value in the subscript of this lowercase z, then z sub p is defined in such a way that the probability that the standard normal random variable is cap z is greater than z sub p is equal to p. So you can see here that this probability is the value that is in the subscript of little z. And so if we were to think about z sub alpha over 2, that would be the number on the number line, such that the probability that the standard normal random variable is greater than z sub alpha over 2 is alpha over 2. So that is how we come up with the interval coefficient, and the margin of error is therefore the product of this interval coefficient, which is obtained from the standard normal table, and the standard error of the point estimate. Now let's look at some examples, some interval coefficients that are commonly used, and in particular what we're going to look at are the interval coefficients that would be used for what we might call at this point a Z interval when the confidence level is 90%, also for a 95% confidence interval, and also for a 99% confidence interval. Now, if the confidence level is 90%, and again, let me remind you that the confidence level is denoted this way: 1 minus alpha times 100%. So if the confidence level is 90%, that implies then that 1 minus alpha is equal to 0.9. And so what is alpha? If 1 minus alpha is 0.9, then alpha is 0.1. Now we need alpha over 2 for a two-sided confidence interval. So what if alpha is 0.1, what would alpha over 2 be? Well, it would be 0.05. Okay? And similar, and now we're going to find out this value in just a moment. Now what would, let's suppose that the confidence level was 95%. Well, if that's the case, then 1 minus alpha is 0.95. That implies that alpha is 0.05, which in turn implies that alpha over 2 is 0.025. And so the alpha over 2 in the subscript would be 0.025. And then finally, if the confidence level were 99%, that would imply that 1 minus alpha is 0.99, which in turn would imply that alpha is equal to 0.01, and so alpha over 2, which is the subscript of this interval coefficient, would be 0.005. Now let's determine these values. Let's start off with the middle one. Let's start off, suppose that the confidence level is 95%, so that alpha over 2 is 0.025. Now remember, what this means is that the z sub alpha over 2 is defined in such a way that the probability that z is greater than z sub alpha over 2 is alpha over 2. So if alpha over 2 is 0.025, this is a value on the number line such that the probability that z, the standard normal random variable z, is greater than that value is 0.025. Now let me bring up the standard normal table that we have for this class, and this is the CDF table. This is a left-tailed table. It gives us left-tailed probabilities. And so if the right-tailed probability, which is what we're looking for here, is 0.025, that means that the left-tail error would be 1 minus that, or 0.975. And so what we need to do is to look in the body of the table until we find probabilities equal to 0.975. And if I scroll down the table, I see that I get a probability, a left-tailed probability of 0.975 when z is equal to 1.96. And so what that means is that this value, z sub 0.025, is 1.96. So that would be the appropriate confidence or interval coefficient if the confidence level were 95%. Now let's look for this value here. So if the confidence level was 90%, then that means that alpha over 2, the subscript of this interval coefficient, would be 0.05. Now, again, that is the right tail area. So in this table, what we need, which gives us left-tailed areas, what we would need to try to find is a left-tail area equal to 0.95, 1 minus 0.05, so 0.95. And we don't see 0.95 in the table exactly. What we see are two values on either side of 0.95, 0.94950 and 0.95053. The corresponding z values are 1.64 and 1.65. Now, notice that 0.95 is almost, but not quite, but almost exactly in the middle of 0.94950 and 0.95053. And so we could really use either 1.64 or 1.65, but because we're going to be using this value so often, for example, when we're calculating, when we're constructing 90% confidence intervals, and we'll also be using this z-value in the context of hypothesis testing for our critical points, we're going to go ahead and get a better value, a better z-value than either 1.64 or 1.65, and we're going to get that by interpolating between these two values based on the fact that the left-tailed probability that we want is almost right smack dab in the middle of those two values. And so, as it turns out, the z-value that we're after would be 1.645, so right in the middle between 1.64 and 1.65. Okay, and then finally, for a 99% confidence interval, alpha over 2, the subscript of our interval coefficient, is 0.005. Again, that is a right-tailed area, and so the left-tailed area would be 1 minus that, or 0.995. And so what we need to do is look through the table until we find a value of 0.995 or close to that. And when we look through the table here, we see we don't find 0.995 exactly. We see two values, again, that bracket 0.995. We have 0.99492 with a corresponding z-value of 2.57. And we have 0.99506 with a corresponding z-value of 2.58. Now, again, 0.995 is almost, but not quite, exactly in the middle or between these two values. And so what we're going to do, because again we use this interval coefficient fairly frequently, what we're going to do, instead of using 2.57 and instead of using 2.58, we're going to interpolate to get a better z-value, which would be 2.575. So those are the three interval coefficients for these confidence levels. And so if we look here on the next slide, which you don't have in your notes, but you can copy it down, all right, then these would be the z-values. So this is how you find z-values for a given confidence level. Now, if I were to ask you for the z-value of the interval coefficient for an 80% confidence interval or an 85% confidence interval, you should be able to find that using a similar procedure. Now let's talk about confidence level versus precision. Now, the confidence level and the precision of a confidence interval are inversely related. Specifically, increasing the confidence level increases the margin of error and therefore increases the width of the interval, thereby decreasing the precision of the confidence interval. Decreasing the confidence level decreases the margin of error, which decreases the width of the interval and therefore increases the precision of the confidence interval. So it's important that you understand the relationship between a confidence interval width and the precision of the interval, and also the confidence level and the precision of the confidence interval. So that is the overview of estimation, point estimation, and confidence interval estimation. I'm going to stop the video at this point. In the next lecture video, what we're going to do is look at the relationship between hypothesis testing and confidence interval estimation. There's a very interesting and useful relationship between those two different kinds of procedures.